All right, next up, we're going to do a little investigation into seed preparation. Our next presenter on flaking mill, optimizing performance in oilseed applications. Our presenter is Doug Reuscher. Doug is an applications engineer for CPM, Roskamp Champion, with 18 years of experience in the industry. His duties include sales, startup, training, and support of the equipment. Doug's challenged to be an expert in all phases of our equipment, a really strong veteran member of our team. He graduated from Iowa State University with a Bachelor of Science degree in Industrial Education and Technology. And with that, Doug, take it away.
Good morning. My name is Doug Reuscher. I'm an applications engineer for Roskamp Champion. And today I'd like to talk about optimizing flaking mill performance in oilseed applications. If you have any questions, please send them to my email address at the bottom of the screen. Before we talk about the flaking mill itself, let's talk about safety. If you're going with a tool to open a machine to work on it, you must lock out or tag out the machine before entering to remain safe. Now let's discuss the purpose of flaking, which is to improve extraction results by increasing the surface area, reducing the distance solvents must travel, and rupturing cell walls. We're taking a particle that has an area to volume ratio of approximately 50:1 and reducing it to an area to volume ratio of approximately 200:1. Again, this is to reduce the distance solvent must travel. We want to always operate the flaking mill at or near full capacity. We need to maintain a uniform feed distribution, which will allow us to maintain a uniform roll temperature, maintain uniform roll wear, and prevent roll-to-roll contact. We want to balance the feed rate and roll pressure to obtain the desired flake thickness and motor load. Do not run the flaking mill below 70% of the rated capacity. So if your plant capacity changes, don't simply throttle back all the flaking mills. If you're getting 70% or lower in capacity, then you need to look at turning off a flaking mill or two. We want to compare the seed or crack temperature to the roll temperature with an infrared device. When the roll temperature is within 7 to 10 degrees F of the crack temperature, the rolls are considered fully loaded. Any upset in this condition may cause the rolls to form hot spots. The roll bearings require lubrication. We use the 232/48 bearings that has an L10 life in excess of 100,000 hours with proper lubrication. We recommend that 10 to 12 ounces of grease be added every 30 days. The bearings should be purged annually. Check bearing temperatures weekly. Idler bearings require 1 to 2 ounces every week. Other bearings require 4 to 6 grams monthly, such as the feed gate. And always use a high quality lithium-based grease. From the factory, they're filled with Mobile XHP 222. If you're going to change grease, make sure that it is compatible, or purge your bearings before you change the grease. This is an assembly view of the adjustable roll. We have the cover off, and annually it's necessary to remove that cover and to purge all the old grease because the grease will harden over time, and even though you're greasing it, if that hardened grease blocks the flow, the grease will not enter the bearing. For the drives, we look at alignment and tension. The inner roll drive belt tension is maintained hydraulically. We'll set the belt tension to 150 to 200 psi on the control console. The inner roll drive belts will typically last 3 to 5 years with proper tension. The high torque drive main drive belt should track towards the motor side. It's easier on the motor bearings. We need to check the drive belt alignment every 30 days. And the drive belts typically last 7 to 10 years with proper care. This is a picture showing the inner roll drive side. It's our current design. Our long span is on top, so we're pulling back on this arm to tension our long span. When this arm bottoms out on the hydraulic cylinder, it's time to change belts. We always want to change belts as a full set. This is the hydraulic control console. This pressure reducing valve adjusts the inner roll drive belt tension, which is displayed on the leftmost gauge. Then we have left and right roll pressure, which is controlled by these pressure reducing valves, and the feed gate pressure. For the main drive belt, we need to check for a 1/2 inch deflection at 25 pounds of force. We do that by measuring the long span of the belt and checking deflection at the center. Two situations that we have to have in order to make uniform flakes are the rolls need to be in parallel. If you look down on the rolls, they should be even from end to end to ensure that you're making a uniform flake. The rolls also need to remain in tram, so that means they're in the same plane. So as you're looking directly on the rolls, they are in line. Some of the factors that affect roll profile are roll shape, which is affected by wear, roll deflection, which is most affected by roll proportions. Deflection is more significant at higher pressures. Roll temperature is most affected by feeding. Roll temperature is also affected by roll shape. Some possible sources for uneven roll temperatures are uneven feeding, which is due to buildup, such as in the hoppers, by the feed gate, and in the feeder housing. Agglomerations, which are often found behind the feed gate, in the roll nip, in the finger guards, and in the flow directors. You need to check the scrapers for any wear and make sure that they're not contacting the scraper stops. If the scraper assembly is connecting the scraper stops, then they're not sufficiently cleaning the rolls. Look for any and eliminate any dust accumulations on the scraper blades, flow directors, roll housing, cheek plates, and doors and covers. Rolls operating near full capacity, we need to cycle the roll pressure on every 2 to 4 hours to maintain a more consistent pressure or temperature from end to end. You can think of this as starting a mill out when it's cold. The roll is a certain diameter. As it heats, it grows. If the rolls are not cycled to accommodate that growth, then you'll get roll-to-roll contact and develop hot spots. These are pictures showing dust accumulation. You can see if dust is not cleaned out from the machine every shift, it will accumulate, and that rides on the roll and causes a hot spot, which will make uneven flakes. We recommend that aspiration is from below the flaking mill. So the cracks come in and we have our aspiration at the top of our machine. So we use gravity to help clean the dust, help sweep through the whole machine. So why do rolls wear unevenly? And it's because heavy impurities such as sand and mineral feed down the center of the roll where roll wear is increased. So the center wears more, but we say that the roll ends become high. Okay, and when the roll ends become high, we have excessive pressure on the ends of the rolls. Flakes become measurably thinner on the roll ends. The roll end temperatures become measurably high. The roll ends will spall or form pressure bars. And the rolls are just like a tire. A tire is round, but it is deformed where it touches the ground. It has a flat spot. Our rolls are the same way, where they contact, they flex, and continual flexing can lead to work hardening of the rolls. A couple different types of roll material. On the top, we have a chilled iron roll that has a hard surface and a softer gray iron core. These can either be a static cast or a centrifugally cast roll. On the bottom is an indefinite chill roll. These rolls are more resilient, and it's essentially the same material from the surface to the core, and they can also be static or centrifugally cast. So chilled iron rolls may spall, or they may form pressure bars if subjected to high pressure metal-to-metal contact. On the other hand, indefinite chilled rolls are highly resistant to spalling, but may develop pressure bars if subjected to metal-to-metal contact. To correct pressure bars, it's often necessary to remove all the work-hardened material, which may extend into the roll face 10 to 50 thousandths or more. When grinding rolls to correct pressure bars, rolled hardness should be checked to ensure all work-hardened material is removed. Spalling damage, on the other hand, cannot be repaired. The rolls must be turned and or ground to remove all damaged material and prevent further crack propagation. This is an indefinite chill roll showing characteristics of washboarding. They start with a hard spot on one end of the roll, and if not relieved right away, that hard spot will transfer across the full length of the roll. Chilled iron rolls, however, are a little bit harder, and if the ends get hard and not relieved, the end can break off. So for roll end grinding, how often do we need to grind the ends? And every 4 to 6 weeks is typical. We must check flake thicknesses and roll temperature daily. So how much do we remove when we grind the ends of the rolls? And the minimum taper width is 3 to 4 inches and 2 to 3 thousandths deep. However, each facility is a little bit different on how the machine is fed, so a taper width of 10 to 16 inches is not out of the ordinary. So for roll end grinding, how long do we need to grind? And 1 to 4 hours per machine is common. We do more frequent grinding, will require less total time required. So for roll end grinding, we do this to eliminate high pressure roll-to-roll contact. We first clean off the dust from the machine and block the scrapers off the roll, paint a stripe across the roll, and briefly touch the rolls together to check for actual roll-to-roll contact. This is a form that we give you to fill out where you would note the machine, the pressure on the left and right side, the amp draw from the main motor, inner roll drive tension, the crack temperature, and take 9 temperatures across the end of the roll, noting the flake thickness on the left, center, and right side, and then record any abnormalities. Then maintenance can check over time and see that the temperature is getting higher at the end of the rolls. The flakes are getting thinner at the end of the rolls, indicating a need to grind the rolls. So using the information, and the information is only useful if it's utilized. High temperature and thick flakes would indicate excessive feed rates. High temperatures and thin flakes indicate insufficient feed rates, uneven feeding, uneven roll wear, or a hot spot. And hot spots have a specific cause, and they are excessive feeding, obstruction in the feed stream, roll diameter change, or scraper malfunction. So when we grind the rolls, we paint a stripe along the ends and we touch them together, and where the paint is rubbed off is where it needs to be ground. Here you can see that the end is a high spot and needs to be relieved. So we go ahead and grind the roll, paint another stripe, touch the rolls together, and you can see that it's been sufficiently relieved. So the roll has been relieved at the end sufficiently. For full face grinding, how often is that needed? And the answer is every 12 to 24 months. How much do we remove when we full face grind? And 8 to 10 thousandths is a typical minimum just to clean up the roll. 20 to 50 thousandths or more may be required to correct taper. 40 to 50 thousandths or more may be required to correct washboarding. So how long do we need to grind the rolls for? And typically 8 to 12 hours is pretty common for a typical cleanup. However, 40 to 100 hours or more may be needed to take care of severe washboard or severe taper. And again, more frequent grinding equates less total time required to grind. Here's another example. We told the customer to paint a stripe across the roll. They painted the whole roll, which gives a good visual. They touched it together. Any place that the paint is rubbed off is a high spot and needs to be ground. And you can tell that this roll has severe washboarding. This is an illustration of our roll surface grinder mounted to the rear of the flaking mill. The roll surface grinder can be used to grind the ends of the rolls or full face. We have a slow down drive available to slow the rolls down to approximately 30 RPM, which aids in more rapid stock removal if you have damaged rolls such as a severe taper or washboarding. So to manage the wear, we must measure the roll diameter and shim as required to keep the rolls centered in the machine. When the machine is new, we're feeding directly into the nip of the roll. The back roll is a fixed roll, so as it wears, that nip point is moving back into the machine. In order to keep that centered, we must put spacers in it to keep it centered in the machine. Also, because the roll diameters change, we must replace the cheek plates with new part numbers that are cut to fit smaller diameter rolls. We must also restore the roll end chamfer to the 3/4 inch by 30 degrees as when they were new. We need to also maintain bearing housing to top tension member clearance of 8 to 10 thousandths cold and 6 to 8 thousandths hot. This is a chart showing our 32-inch machine, showing the different roll diameters and the corresponding cheek plates, cylinder shims, rear shims, and the distance that was added to that stroke. So a word about cheek plates. We want to prevent any material from leaking around the ends of the rolls. However, to account for 0.1% increase in white flake fat, a 3284 flaker would have to leak over 2 tons of cracks a day to increase the white flake fat 0.1%. So the moral of the story is don't run the cheek plate down against the roll and carve into it, okay? There should be a 10 to 20 thousandths gap between the cheek plate and the roll face, depending on what seed you're flaking. We also need to look at the scraper blades. The original equipment are 1/4 inch thick, and they must match the width of the machine itself. If the scrapers are too short, they will cut into the face of the roll. If they're too long, they will cut into the ends of the roll. Any questions?
Thanks a lot, Doug. What a great look into the preparation side of seed preparation. A couple questions for you here. The first one, what is special about lithium grease, and is there any possibility of grease coming into contact with the seed?
Yes, that's a good question. Lithium grease has a good temperature. It doesn't break down at a low temperature. So we've been using lithium grease in most of our equipment since I've been here, and specifically in our flakers since about 2009. It offers good compatibility with other greases that are used in the plant. As far as the possibility of it coming in contact with the product, there is a chance. Over the years, we've changed how we've greased our roll bearings. And in the past, we've greased from the outside in, so a little bit of grease could be getting in there. However, if that's a concern, a food grade grease could be looked at for that application.
Great. So another question, really general question. Give us a couple of elements of seed preparation that go into making a good flake. What's done to the seed? You know, what are some things of that crack as it comes in? What makes for good flakes?
You bet. We want to properly condition. Let's talk about relating to soybean. We want to properly crack and condition soybean so it's pliable. If you don't have the right temperature and moisture to condition that, it's going to take more horsepower to make a good flake, even if you can make a good flake. And also, if it's not conditioned enough, you may be making a lot of fines, which are undesirable.
Great, great. Well, that is all the questions. Thanks a lot, Doug. Appreciate your time.